Hi, welcome to lesson 2 of unit 8. You are the Imagineer. So we're going to start with this ready problem. The black curve in the graph shows the graph of f of x equals sine of x. And part A says write the equation for the green dotted line labeled g of x. So g of x, we see there's a 2 here. So that means g of x is equal to 1. It's a horizontal line. Write the equation of the purple dotted line. H of x, again, we see a -2, so we know our scale is counting by 1, so h of x, another horizontal line, is equal to -1. So it says, list everything you notice about the graphs of f of x, g of x, and h of x. So we notice, I don't need to write that word, so the graph of f of x fits between the graphs of g of x and h of x. The maximum values of f of x fall on g of x, not h of x, fall on g of x, and the minimum values of f of x fall on h of x, right? So we see that right here, right? Those are sort of the minimum values falling on the graph of h of x in the maximum, right? So local max, local min, and so on. I could do that for all of these. Okay. Question 2 says, the black curve in the graph shows the graph of f of x equals sine of x once again. So part A says, write the equation for the purple line labeled m of x. So m of x, another horizontal line, so m of x equals, we see there's a 3 there, so m of x equals 3. Okay. Sketch the graph of f of x times n of x. F of x, well, we know that is f of x is sine x, sine of x, and m of x equals 3. So really, f of x times m of x is 3 sine of x, right? That's what we get when we multiply those. So that's going to, basically, all our zeros, when we multiply this by 0, these are going to stay exactly the same. Those zeros, 0 times 3 is still 0. I was just seeing if they gave us any more space. But all those maximum values of 1, those are going to become maximum values of 3. 1 times 3 is 3. So here we have the points 3 up here. So it looks like it's going to be, I'll label it after. And all our minimum values of -1, those are going to go down to -3, which we don't quite have. It didn't really actually give us the space for it. So I'll kind of just do it down here, right? And I'm looking at it does not give me another graph to work with. So this is the graph we got. So, and this 0 here. So I'm going to go up towards this 3, back to 0, down towards this -3, back to 0, and it's going to follow that same pattern. So it expands our graph. Okay, and I'll label these. So this is pi over 2, 3. And these are still just pi 0 and 2 pi 0. And 0, 0, those don't change. But this becomes 3 pi over 2, -3. And here we have the point. Let's put it up in here, I guess. -pi over 2, -3. -pi 0, 3 pi over 2 positive 3 and negative 2 pi 0. So that's how that graph is transformed. So it says write the equation of f of x times n of x. Oh, well, we already did that off to the side. We get f of x times m of x equals 3 sine of x. Okay. Would the line y equals 3 also be a boundary line for your sketch? Yes, it would. Since the minimum value of the graph of f of x times m of x is y equals negative 3. Or I should say the min values touch. Values touch y equals negative 3. Okay. Question 3. The black curve in the graph shows the graph of f of x equals sine of x. Write the equation for the purple line labeled b of x. So here we see negative 2, so b of x must be equal to negative 3. So let's get to the graph of f of x times b of x. Part B asks us to do. So it's super similar. Anytime we have a 0, it's going to maintain the 0. Negative 3 times 0 is still 0. So our zeros are not going to change. 0, 0, pi 0, and 2 pi 0. However, our maximum values, when we multiply those by negative 3, this positive 1 becomes a negative 3. So that goes all the way down here. So it changes direction here, right? So this becomes negative pi, oops, sorry, not negative, positive pi over 2, negative 3. And here, where this was a minus 1 times minus 3 becomes positive 3. So we have 3 pi over 2, 3. And our graph continues that way. So same thing here, this point becomes negative 1 times negative 3, which is positive 3. So negative pi over 2, positive 3. And this maximum value turns into a minimum value. At negative 3 pi over 2, negative 3. So part C says, what's the equation? Well, we multiplied by negative 3. We multiplied sine of x by negative 3. So the equation just becomes negative 3 sine of x. How is the graph of f of x times u of x different from the graph of f of x times m of x? Well, the maximum values and the minimum values are the same, but the direction has changed. This is the direction changed. Since instead of saying the graph, I'll be more specific. Since f of x times b of x, the one we just did, is reflected over the x-axis by multiplying sine of x by a negative. That's what we did. We reflected it over the x-axis. So will the line y equals 3 also be a boundary line for your sketch? Yes. Since the maximum values of f of x times b of x touch y equals 3. Okay. You could also say they're tangent to because they only touch in one place. y equals 3. Just make that a little neater. Okay, let's go down to problem 4. So problem 4 tells us that f of x is equal to x, g of x is equal to sine of x, and then h of x is going to be the addition of those two, f of x plus g of x, or if you want to write it as x plus sine of x, you can. So that's what h of x is going to be. And it says fill in the values for h of x in the table. So if we go down here, it gives us a table. Notice it predetermined which x values we want to use, and it told us basically the decimal approximation of these. Remember, f of x is equal to x, so we just see negative 2 pi is roughly negative 6.28, so it's just the decimal approximations. These, g of x is equal to sine of x, so here, when we do sine of negative 2 pi, we get 0. So it's already filled all those in. Now it wants us to find h of x. So really we just add f of x and g of x. So not too bad, since we have a bunch of zeros, ones, and negative 1. So negative 6.28 plus 0 is still negative 6.28. Negative 4.71 plus 1 is negative 3.71. Negative 3.14 plus 0 stays negative 3.14. Negative 1.57 plus negative 1 is negative 2.57. 0 plus 0 is 0. And here we get 2.57. 3.14 plus 0 is still 3.14. And here we get 3.71 when I add those together. And 6.28. So we should see some symmetry. If you notice, we have a bunch of negative values here, 0, and positive values. Those are the same absolute value that we see above. So there's symmetry here, which makes sense because the sine of x is periodic. So there is repeating values. Okay. Now it says with a smooth curve. So we're going to connect everything. Graph these functions. So we have a bunch of ordered pairs, right? We have negative 2 pi, negative 6.28, or negative 2 pi about negative 2 pi. So here's negative 2 pi. Looks like 6 is probably, so 1, 2, 3, 4, 5. It's going to be off our graph a little bit. There we go. I'll label it negative 2 pi, negative 6.28. That's that point. Okay. Then we have negative 3 halves pi. So that's going to fall, right? We have 1, 2, 3, 4, 5. So that's going to fall right in between. So negative 3 halves pi is about here. And remember, the value for that is about pi is negative, wait, where are we? Negative 3.71. So just above 4. Okay, so that's negative 3 pi over 2, negative 3.71. Okay, our next point is negative pi and negative 3.14. So here's, I might have graphed that way too high actually now that I'm looking at what they're counting by. Let's just move that down a little because I just put negative 3 on the graph. So we're just going to move that down a little bit. That's fine. Okay. So negative 3.14 is just above that line, and that's going to fall on pi. So let's say that's about here. So negative pi, negative 3.14. Okay, negative pi over 2, so it's going to be about right here. Negative pi over 2 is just above negative 3. Negative pi over 2, negative 3, negative 2.57. Okay, now 0, 0. That one we can do pretty cleanly. 0, 0. Okay, and then we have positive pi over 2. So that's about right there. And positive, let's see, this is where 1 would be. So here is roughly 3. Right? So we have 2.57. That's probably good. Pi over 2, 2.57. And then we have with pi and 3.14. So pi and about 3.14. Three pi over 2. And 3 point, and just above 4, just below 4, I should say. So about there. And lastly, 2 pi and roughly 6. So again, that's going to be off our graph. So 2 pi, 6.28. Now let's actually connect these with a smooth curve. So this curve, it does an interesting little thing here. It has a couple little inflections. And mine's not perfectly to scale, but it's pretty accurate. So we see a few different little inflections here. Okay, that's roughly pretty accurate, and it should look similar in that first quadrant and in that third quadrant. Okay, let's go to question 5. It says f of x is x, g of x is sine of x, and this time instead of adding them, it wants us to multiply them. So f of x times g of x, which is x times sine of x. So let's fill in the table. So remember we're multiplying. Multiply f of x times g of x. So anything times 0, it's going to give us 0, or any real number times 0. Negative 4.71 times 1 is still negative 4.71. We get times 0 again. Let's fill in all our zeros. Make that quick. Anytime we have a 0, those are going to have a product of 0. Here we're multiplying by negative 1, so it's going to change to positive 1.57. Here we have a positive 1, so it stays positive 1.57. And here this goes to negative 4.71, since we're multiplying it by negative 1. Okay, so now it wants us to graph these points. So let's start putting them down. So we start with negative 2 pi 0, right there. And then we had negative 3 pi over 2 and negative 4.71. So negative 5 is about here, right? So negative 5. So let's say somewhere around there, right? Negative 3 pi over 2, negative 4.71. And I have a point that's symmetric to that on the opposite side of the axis. So let's go and put that down first. We don't have to go in order, right? This is 3 pi over 2, negative 4.71. So those two are already plotted. Let's plot all our zeros as well. Why not? Right, so we have negative 2 pi 0. We also have negative pi 0. And we have 0, 0. We have pi 0. And we have 2 pi 0. So all our zeros are done. So we plotted all of these. And now we only have negative pi over 2 and about 1.57 left. So negative pi over 2, 1.57. Well, 1 is here. So maybe right about there. So negative pi over 2, 1.57. And positive pi over 2, 1.57. Okay, so I have all my points down. Let's connect these with a smooth curve. That could look a little smoother. Let's do a better job there. Now, I stopped at 2 pi and negative 2 pi, but we know that sine of x doesn't actually stop here, and it is periodic, so it's going to repeat itself. So that's one full period or one full pattern. So it would just keep repeating, which means the next thing it would do would be to continue to go up a little bit. So I'm just going to kind of go like that to show that it will continue off to the sides. Okay, and there we have it. Question. It says the next set of directions, I'll read those first. Match each equation below with the appropriate graph. Describe the features of the graph that help you match the equation. So we have, where are our equations at? There are our equations, and there are our graphs. So we're going to have to do, I'm going to pause and take a screenshot, put these side by side for a second. Okay. So let's start. You can start by looking at the graph and finding the equation, or vice versa. I'm going to start by, I guess I'll start with looking at the equation and trying to find a graph. So, and this got cut off. This is the absolute value. I'll put that there, of x squared minus 4. So we're definitely looking for something that looks like a parabola. However, so this is going to be the shape of a parabola, right? So part of the shape will be a parabola. Parabola with no negative values, right? Negative values because of the absolute value. So since we're looking at absolute value, let's find a graph with no negative value. So here we see it goes into the negatives. So this one has no negative values, but it doesn't quite look like a parabola. Here's negatives. So the only two ones that actually kind of fit the absolute value part, there's no negative values here, are C and F. But F has that parabola shape as well. So F is going to be our graph of f of x. So graph F, and I'll write the equation, minus 4. And we do see the two x-intercepts at 2 and negative 2, so you could also use the x-intercepts to help you just reconfirm, right? I'll add that. X-intercepts at x equals 2 and x equals negative 2. And to add the y-intercept is often a really good one to look for as well to confirm that y-intercept. So this one has a y-intercept of 4. If we plug in 0 for x there, we do get a y-intercept of 4. So I'm going to add that in there. Let's see. And a y-intercept of 0, 4. Okay, good. So let's look for our next equation, negative x plus 5 sine of x. So this is definitely going to have some periodic characteristics, but let's focus on this. So remember, sine graphs have a midline. So the midline of this graph will actually be, remember the midlines are added at the end of this, so the midline of this graph will be y equals negative x. So we're actually looking for something that looks periodic. So periodic on both sides, but it is, so I'll just put periodic. So it's a periodic function with that midline of y equals x. So here, this is not periodic. We don't see things repeating itself. B certainly looks like it could be it, so let's definitely keep B in mind. C, it does have some periodic tendency. We see some replication, but we're not seeing that y equals x come up here. We're not periodic. And here we're not seeing, we're all seeing a little bit of symmetry here, but we're not seeing the sine function that we need to necessarily see. It looks like a sine function, so this definitely has sine of x tendencies, where we have this 0, 0 point here. But B is definitely our closest match, where we see that y equals x being the midline. So let's B, y equals x. And it doesn't hurt, we can add, goes through 0, 0. That's not going to distinguish it from all the other graphs, but we still see that point. Yeah. Okay. Let's move on to our next one. Again, we see a sine function here, but notice a lot of our graphs have a feature of sine. A few of them have a feature of sine. So we're not just looking for periodic. So F, we've already matched. And B, we've matched to negative x plus 5 sine of x. Okay. Let's undo sort of some of the markings we have on these other ones. So let's look at 4 times the absolute value of sine of x. So it's going to definitely be, so it's a periodic function. We see that sine form, but all the negative values, so no negative output values due to the absolute value. We haven't been paying much attention to the amplitude. Let's look at that. It will have an amplitude of 4. And it should still pass through. It should still pass through 0, 0, right? If I plug 0 in for sine, I get 0, and the absolute value of 0 is 0 times 4. I still get 0, 0. So let's look at which graph matches those attributes. Well, again, we already kind of looked at which graphs don't have the negative y values, and we landed on C before. Again, C definitely has some periodic tendencies. So, and we see that that amplitude of 4, that maximum value of 4, our amplitude. So I should kind of be careful with this word amplitude. Let's say max value. We'll call it maximum value of 4. Oops, and I moved my sheet a little. Let me just undo that. Okay, so this is graph C, 4 absolute value sine of x. Okay, so the only positive outputs is definitely one of the number 1 clues into that one. Graph, our next one, d of x, says 10 minus x squared plus 5 sine of x. So we're seeing this quadratic piece of this parabola piece, and we're seeing this periodic piece of it. So let's think about the y-intercept, I guess, on this one, because this 10 kind of stands out clearly. Remember, the y-intercept of sine of x is 0, and of x squared is 0, so this y-intercept, if I'm adding 10 plus 0 plus 0, the y-intercept should be 10. 0, 10. So that might be a quick way to eliminate a bunch of graphs, because I definitely don't have a y-intercept of 10 here. We already matched this one, but we see that's not 10 either. No y-intercept of 10 here. And no y-intercept of 10. So right here we have a y-intercept of 10. So that information is enough by itself just to say, hey, this must be A. 10 minus x squared plus 5 sine of x. But let's look at some other things, right? We should see a parabola. Should see characteristics of a parabola. Characteristics of a parabola. And not only of a parabola, but since it's negative, of an upside down parabola. Which we do, right? We see that upside down parabola right there showing itself. And those two characteristics are enough to really identify. We only needed one of them, but now we have sort of two characteristics that help us identify that graph as A. So we'll move on from there. There's some other things we can point out, but that's pretty good. So we have two graphs left. We have D and E. So we have negative x times 2 sine of x. So this one has a sine aspect of it. It should have some periodic tendencies. And this one does not, right? This one is an absolute value plus a linear equation. So let's look at w of x first. Negative x times 2 sine. So this one, remember, what I want to focus on is this x is being multiplied by sort of the amplitude. So the amplitude will change. The amplitude will get larger as x increases or increases towards infinity. Actually, I'll phrase it as x approaches positive or negative infinity. I'll phrase it that way. As it's going left or right, we should see this increase get larger and larger because we're multiplying by x. And if x is closer to 0, let's say x is 1/2, then the amplitude grows smaller. So that's one thing we can look at with the two graphs remaining. And we're seeing that here, right here. That graph is sort of growing as we go. And notice it's negative too. So normally where our sine function would start at 0 and starts increasing right away, we do see that we have some decreasing tendencies on this graph where we don't see that on this graph. And we should see a y-intercept. I'm going to add that y-intercept of 0, 0. So we only have two graphs left. We definitely don't see a y-intercept of 0, 0 here. And we do see one here. So this is definitely going to be graph D. Negative x times 2 sine of x. And that leaves graph E here, right? E is 2x minus 4 plus the absolute value of x. So let's break that equation down, see how we could recognize it though. So this last graph is basically all linear. So looking for linear, for all linear pieces, I suppose I'll call them pieces, right? So when we have a negative value of x, so negative values of x on the left side of that y-axis, so this is showing an increasing function, which is good. So normally with the absolute value, it looks like a v, right? But because we're adding on to, if I have a negative value of x, anything beyond negative, or x equals 0, I should say, we're going to be down below. And let's look at the y. Let's look at our y-intercept. Sorry, I'm phrasing this poorly because I'm trying to look at the graph at the same time. So our y-intercept, if we plug 0 in for x, right, we get negative 4 plus the absolute value 0. So y-intercept of 0, negative 4. And I don't think that was our only one with 0, negative 4. Maybe it was. I can't remember. Yeah, it is our only y-intercept of 0, -4, we had a 0, +4. So that's a huge clue right there, that our y-intercept is 0, -4. But that linear piece is really important. So it doesn't look quite like an absolute value graph, but that's because we are adding this 2x minus 4 to it, which does allow it to sort of have negative outputs down there that are below -4. So that is okay for that one. All right. Question 7. The chart names 5 families of functions and the parent functions. The parent is the equation in its simplest form. In the right-hand column is a list of key features of the functions in random order. Match each key feature with the correct function. A key feature may relate to more than one function. Let's see if it goes on to the other page. Nope. So this is all our key features. So I'm going to zoom up nice and big here so we can see it all. Okay. So I think the best way to do this is to read each sort of key feature at a time and then figure out which ones it applies to, rather than rereading these key features over and over and over. So A, the ends of the graph have the same behavior. Well, that's definitely not linear. Those are ending in different directions, but quadratic, yes, that is absolutely true for a quadratic function, since it's an even function. Really, any even function, that will definitely be true. So it's not true for cubic. Exponential, nope, one end has an asymptote, the other one is going to approach infinity or negative infinity. And then rational, yes, this is true. The ends of the behavior are both going to approach a asymptote most of the time. Now, that being said, this isn't true all the time. So let's see, key feature may relate to more than one function. This is true sometimes, so we'll put it down. It's true sometimes. B. So B is each graph has a horizontal asymptote and a vertical asymptote. Well, linear equations don't have either. Neither does quadratic or cubic. Exponentials have one or exponentials, I should say, have horizontal asymptotes, but they don't have a vertical asymptotes. So this would only be true about B. Now, with a sort of note that, like, I'm going to sort of add or whole. So a rational function can look linear with a whole. But so that one's, again, a little bit of an asterisk on it. So I'm going to put little asterisks on both of these because they can look rational when we simplify them. It ends up being a whole instead of an asymptote. So not every rational function has both of those. C, the graph only has a horizontal asymptote. So that's going to be our exponential C. Linear, quadratic, and cubic don't have any asymptotes at all. In rational functions, I should say could be C, but B and C seem like they're conflicting each other, so we won't put both. Okay, part D. Part D reads, these functions either have both a local maximum and minimum, or neither a local maximum nor minimum. Okay. So linear is out because it doesn't curve at all. So if there's no turning points, so there definitely needs to be turning points here. So a quadratic has always a absolute max or min. So it doesn't fit a quadratic. But a cubic, this does fit a cubic. So D, right, it says either a local maximum or minimum. So if it's a cubic, it could look like this, right? And then it has both local max and mins. Or it could look like this and only has an inflection point, in which case there's no local max or mins. Local max and local min. So that's what D is. Okay, so let's move on to E. E says the graph is usually defined in terms of its slope and y-intercept. Well, hopefully that is screaming linear to us. No other graph on this has a slope. They each have a rate of change that we could identify, but none of them have a constant rate of change, so only linear for that one. Okay, F. The graph has either a maximum or a minimum, but not both. So that is a quadratic function. So, right, a quadratic function either has a maximum or a minimum, but not both. Again, there needs to be a turning point for this one to be true. A cubic has both or none. Linear has no turning point. Exponential is a curve but no turning point. And rational, again. So let's go. Now, some rational functions can have quadratic natures, actually. Because rational functions can look a lot of different ways, but that's too strong of a statement to add to rational. So let's go to G. As x approaches negative infinity, the function values approach the x-axis. So as x approaches negative infinity, right? So as we're going to the left, our graph is approaching the x-axis. Well, this is true for an exponential. That's basically describing a horizontal asymptote. And rational functions can also have that horizontal asymptote. Okay, let's spread that a little more. So, again, rationals look so many different ways. So H, the ends of the graph have opposite end behavior. So that is true for linear and cubic. When it says opposite end behaviors, I wouldn't put that on exponential because one end is approaching infinity or negative infinity, the other end's approaching an asymptote. I wouldn't really call asymptotes and infinities opposite. The same thing with rational. Typically, it's approaching an asymptote. So let's just do that linear and cubic for H. I, the rate of change of the graph is constant, right? That's just another way of saying it has slope, which is linear. So linear equation has slope, so that's I. Nothing else has a constant rate of change. The rate of change of the graph is constantly changing. Well, that's true for everything else other than linear. So all of these have a rate of change that constantly changes. So J goes to every single one of these. So J, everything but linear. Okay, K. This graph has a linear rate of change. So let's think about that statement. Really, that's talking about sort of the second difference. So it's not a constant rate of change. A linear rate of change. So linear, right? Rate of change meaning there is a pattern to the rate of change. So that's actually going to be a quadratic graph. Linear rate of change, because the difference of each difference is constant, right? So constant second difference. Constant second difference. I guess I'll phrase it like that. So that one is quadratic and only quadratic. Okay. L. These functions are of degree 3. Well, that's definitely describing our cubic. Cubic has a degree 3. We see it right here. Okay. The variable is an exponent, m. So that is only true for exponentials. So m, exponentials, our variable is an exponent. Let's go down to n. These functions contain fractions. So we're thinking rational already, with a polynomial in both the numerator and denominator. So polynomials, remember, polynomial can be a constant number. So this is true for n. No asterisks at all, right? A polynomial doesn't have to be a variable. Just like this, 1 over x. So that is a rational function. And then lastly, P says the constant will always be the y-intercept. So that is true for polynomials. Polynomials in standard form. Right, so let's see which ones are polynomials. We have P as a polynomial. Sorry, not P. Linear is a polynomial. Let me create a little more space right here for these two. This is also true for quadratics, often called the C value, right? Mx plus b, so we're thinking the b value here. This is ax squared plus bx plus c, we're thinking the c value. And it's also true for cubics as well. So it's going to be true for any type of polynomial. It's not true for exponential. For that one, the y-intercept is typically the initial value. In rational functions, often that change. Sometimes they do not have a y-intercept because that's where the horizontal asymptote is. But sometimes they do. Okay, and that's it for Unit 8, Lesson 2. Hopefully you found this video helpful. Thank you for watching.